by putting f equal to phi into a vector, where a vector is a constant vector. So by putting f equal to phi a vector in the divergence theorem, we need to show that this volume integral is equal to this surface integral. So we are going to start with the divergence theorem, where we take the surface integral of dot product of f vector with n vector ds, and then we put phi into a vector in place of f vector to show this result. So by divergence theorem, or you can say the Gauss's divergence theorem, we have the surface integral of dot product of f vector with n vector ds is equal to the volume integral of divergence of f vector dv, where it is given that f vector is equal to phi into a vector, where a vector is a constant vector. So just putting f vector equal to phi into a vector, we get the surface integral of phi into a vector dot product with n vector ds. This is equal to the volume integral of divergence of phi into a vector dv. Very fine? Okay. Let's evaluate this first. So the divergence of phi a vector, this is equal to summation I vector dot product with partial derivative of phi into a vector with respect to x. So this is equal to summation I vector dot product with, okay, derivating this phi a vector with respect to x. So this is phi into partial derivative of a vector with respect to x plus partial derivative of phi with respect to x into a vector. Separating the sum, right? Now in the next step, I am taking this phi outside of this summation, and this dot is shifted between these two. So this is equal to summation I vector taking phi outside dot product with partial derivative of a vector with respect to x plus summation I vector taking partial derivative of phi with respect to x together, and the dot is shifted over here, and I'm having a vector over here and taking this in bracket. So this is equal to phi, and this is nothing but the divergence of a vector plus, and this is grad phi dot product with a vector. You can also remember this result. This is the divergence of phi a vector. And now substituting this value in this integral. So marking this as 1 and this as 2, substituting 2 in 1. So this is surface integral, which is equal to the volume integral of divergence of phi a vector dv, and I'm going to substitute the value now. So divergence of phi into a vector is, okay, phi del dot a vector plus del phi dot a vector dv, right? Now because this a vector is a constant vector, yes, and the divergence of a constant vector is always equal to 0, so this first term is 0. So this is equal to the volume integral of the remaining second term. Reason, divergence of a vector equal to 0, as a vector is constant vector. Writing the left hand side also. Now this a vector with dot product can be taken outside of this integral. So this is a vector dot product with surface integral of phi n vector ds. This is one and the same thing. We can also write this integral as this. So this is equal to the volume integral of, now this dot product can also be written as a vector dot product with del phi. And I'm taking this a vector with dot also outside of this volume integral. So here I'm writing a vector and dot product with this volume integral. Del phi dv. So this implies taking this volume integral to the other side and taking a vector dot common is equal to 0. But a was arbitrary. Any constant vector we can take for this. So but a vector was arbitrary, and because it is having its dot product with this complete difference of the integrals, which is equal to 0. Their dot product is 0. So that implies the difference of these integrals is equal to 0. So by Taylor's arbitrary, this implies the surface integral of phi n vector ds minus the volume integral of del phi dv is equal to 0, which implies the surface integral is equal to this volume integral, and this is our required result. Okay, thank you.